and we're going to talk about balance and equilibrium and stress and how to find the balance when we're under stress. So let's begin. I forgot yesterday. Figured we'd ask the Magic 8 Ball. Do you think it will tell us what will happen? Actually, I have a defunct kind of Magic 8 Ball. It's indecisive. It says, rather hazy, try again later. So maybe we should ask a question first. So there's this balance. Some of the things that can help you when you're doing Le Chatelier's principle. Le Chatelier's principle is the idea that there's a stress. So remember, equilibrium means we have a closed system. So something that can help is to put brackets around your system. So it's all in one container. You can't go outside the container. And what we're going to do is we've reached the balance point. So we can all stand here, do the whole thing on one leg, and we stress it. And we have to come back to the balance. So the reaction has to get back to its balance point, and it's going to adjust. All right, so equilibrium's established. All again happens in under a nanosecond and like a femtosecond. So if you guys were actually doing this lab, you mix it and students are like, when do I know it's at equilibrium? It's at equilibrium before you even, as soon as it mixed, as long as everything is there. All right, so the system's at equilibrium. It's a closed system, and you add some more calcium ion. Now remember, I left off some states of matter. If I show an ion, it is aqueous. So it's aqueous. And only two states influence equilibrium, are influenced by equilibrium, which is aqueous and gas. So something that can help is if you see a solid or a liquid, something I mentioned yesterday, whenever you see those, just put a light line through them, because it means they're not going to have an influence on our equilibrium. All right, if we add more calcium, the reaction has to use the calcium. So remember our K expression. Let's go ahead and write our K expression. So K equals, we leave off the solid and liquids. The only thing in the numerator is the CO2. So products on top in the numerator, and then our reactants are in the denominator. So calcium. Remember, this was what I said from the first video. The one thing, hopefully you got more than one thing out of it, but the most important thing about equilibrium is being able to write this expression and to recognize it is our balance point. Now, that 2 came from the coefficient. The coefficient becomes an exponent. So anything with a coefficient actually has the greatest effect on equilibrium because it's an exponential effect. All right, if we add more calcium, the equilibrium has to shift to keep K constant, because that's what K stands for. In German, constant is written with a K. So if you add more of something, think of it as your body, the system has to use it to get back to the balance point. So when you add more calcium, it can't go this way because there's a wall there. So it's going to shift forward. What's wonderful, if everything show your work, is we just use arrows. Or you can say forward or towards the product. Those are the 3 ways you would see. So either with an arrow in the forward direction or towards the product. So it's not saying it favors the product, it's saying it's shifting towards the product to maintain the equilibrium. So the calcium and the bicarbonate are going to react a little bit more to get back to our K constant. All right, B is over here. Now, what if I took away the CO2? Now, the CO2 is a gas, excuse me. So all we'd have to do is pull the cork off, and the CO2 is going to escape. You're no longer at equilibrium. So this is going to have to keep reacting to keep it flowing into the equilibrium. Now, maybe we put the cork back on, but if you take something away, you're going to have to move towards what you took away to keep the balance. So stay on one foot. Keep my balance. All right, if you add something, you're going to react it more. So if we added CO2, it would actually move reverse. Now, if you took away, what would happen if you took away the bicarbonate, which is actually pretty simple to do in lab because this is typically a base. So if we added something like HCl, the HCl would react with the bicarbonate and use it up. And so the system would try to make more bicarbonate. HCO3, remember, is bicarbonate. And so it's going to shift reverse. So on B, we took away the CO2, so it shifted towards the CO2. Here, we took away the bicarbonate, which is a reactant, so it shifts reverse towards the bicarbonate. All right, and then D, if you did my little trick, where we cross out solids and liquids gently, they're there, they're important. The equilibrium is not there unless the calcium carbonate's there. This is a no change. And again, I apologize the lighting. I realize my shadow, it's the morning, so the sun's coming in, so my shadow keeps showing up over there. All right, so there's no change because it's a solid. Now, if you took away the calcium carbonate, completely took it away, it would shift forward because equilibrium, everything's present. All right, so that's the idea. If you add something, it reacts. Unless it's a solid or liquid. And if you take away something, you're going to have to make more. So when I say Chinese medicine, this is exactly what Chinese medicine is. If somebody has an excess, they have too much, we try to get rid of the excess by helping their body to sweat it off. Maybe puke it, right? When I had my mushroom experience, not those kind of mushrooms, the type that make you sick. And all right, let's do this next one. We're deviating. All right, so this one has an extra piece, and I actually am going to mention it with the previous one also. And the extra piece here is that delta H symbol. And so if you've looked at the syllabus, you do see we come back and we study, in fact, we're going to talk about Hess's law today, but we do study enthalpy and entropy disorder, which is truly the only law because enthalpy is a form of entropy and free energy. All right, so delta H is enthalpy. You can be exo or endothermic. All chemical reactions are one or the other. Now remember, everything's two ways. This is saying in the forward direction, the delta H is always for the forward direction. If delta H is greater than 0, oops, sorry, I have a box there. That means it's positive. That means it's endothermic. That means heat is going into it. So we can write heat over here. I lost my blue pen. I think you can see it. We should write it with red for heat. It's too bad the red doesn't show up. Heat. It's giving off heat. It's on this side of the reaction. Whenever we show the symbol delta H, we always show it on the after the reaction. But if it is positive, it means the heat is on this side. So it's absorbing the heat. If delta H was less than 0, negative, it would be releasing heat. Now, delta H's are positive and negative, absorbing, releasing, like your bank account can be positive or negative. K's, however, are always positive because they're a ratio. And that's actually one of the big lessons this whole term. And when we get into endo and exothermic, into thermodynamics, again, we'll relate all of it the whole term, the whole year. Now, I want to go back to this first one. I didn't give you a delta H. We could do like all that fancy math. I'm trying to remember. Calcium bicarbonate actually is endothermic, I think. So heat would be here. And how temperature affects it, we can do it with this one because I wrote the heat in, is we're going to put our brackets. Let's get rid of our red. So the heat is in the brackets. It's on this side. Don't put the delta H in the brackets because the delta H is just telling you where to write the heat in. And you don't have to write heat in. This is something maybe about half of you, maybe I'm being generous there. Maybe a third of you, this will really help. I'm going to tell you a couple different ways you can remember how to do the exo-endo part. But if you write the word heat in, it will be within the brackets, whereas the delta H is outside of the brackets. So if we added more heat, say, it would be the same like what we did up there. If we add heat, it would shift forward. You would have to absorb the heat that you added. So a second way you can remember it, so a lot of students that actually works for them, is heat, high temperature favors the endothermic direction. Endothermic wants to absorb heat. It's like wanting that heat. So heat always favors the endothermic direction. So both of these reactions were endothermic, but in the forward direction, that would mean in the reverse direction, they're equal but opposite, which would mean they're exothermic. All right, let's walk through these. And I'm going to use green. All right, so a fine fairy removes the hydrogen. So she sucks it out to make some fairy dust. So if we cancel out the hydrogen, it's no longer there. We have to shift to make more. So it's going to shift in the reverse direction to make more. Not too bad. All right, a mischievous gnome. You all know what gnomes are. I don't have a gnome in here. That's what I was looking for. They're out in my other room. We'll see them later. Mischievous gnome adds some more H2O. Oh, well, if you were a step ahead of me, and remember H2O here is a liquid. Now, please be careful. In both these examples, the H2O was a liquid. Sometimes it will be a gas. And if it is as a gas, it does definitely affect the reaction. So if it was a gas, it would have shifted it reverse. But here, it's a liquid, so no effect. No change. Nothing happens. All right. A gremlin sits on it and squishes it. Gremlins are really big. I don't have those around here. My dog and then the dog we just inherited, they keep the gremlins away. And so does the cat. So the gremlin sits on it, which means he's squishing it, which means the volume decreases. Whenever volume decreases, the pressure also will increase. Volume and pressure are always inversely related. So as you squish it together, the pressure is going to increase. Now, temperature is independent of this. Temperature is going to be related to exo-endo. So please be careful with that. That is one of the, especially for those of you who just took 222 the first 5 weeks of the summer, that gets so ingrained in you to look at temperature and pressure effect. Here it's totally different. Pressure and volume are related. Temperature is determined by exo-endo. So we'll get to that. It's always a separate question. All right, so you squish it. There's less space. This whole thing gets squished. This is like, you know, in the first Star Wars, technically the fourth, that when they're in that room and they're getting squished, it's going to move to the side that is smaller. Meaning, when you have smaller space, it moves to the side with fewer moles. Now, it's not just any moles. What takes up space? What has pressure? Gas. So fewer moles of gas. That's when you increase the pressure. If we did the opposite, it would be the opposite answer. So we're pushing it together. It's going to move it to this side because there was only one gas. Here we actually have 4 moles of gas because we have 1 plus 3, which you can count on your fingers. So this is going to shift it forward because there's not as many moles of gas on that side. All right, Santa's elf. You guys all know what Santa's elf? Make sure he's checking, make sure we're all nice and not naughty. He likes ice, so he puts it on ice. If we heat it up, it's going to go forward. So we put it on ice, what's going to happen? The opposite. So for most students, the ice question can be challenging. Think of it, okay, if I heat it, what's going to happen? It's going to absorb the heat. It moves in the endo. So ice, it's going to move in the exo. So exo is releasing the heat, melting the ice, moves reverse. All right. So we want reverse, no effect, forward, and reverse. And then E says, Which of these changes will affect the CO and actually increase the carbon monoxide? Well, the carbon monoxide is on the reactant side. So which ones are going to shift it towards the reactant side? Well, that was A and D, because they shifted it reverse. Whenever you see a question like that, first do the forward reverse and then see, does it shift it towards it or not? All right. And then this question, every student's favorite question. What temperature and pressure will shift it forward? So this was what made Haber, got him his Nobel Prize for the Haber process. So making ammonia. So there's 70% of the air that we're breathing is nitrogen. Nitrogen's a triple bond. Our body can't use the nitrogen. Plants can't use the nitrogen, and plants need nitrogen to grow. And Haber figured out how to react the nitrogen and hydrogen to make ammonia. It's not a favorable reaction. And he figured out how to tweak the temperature and pressure to make it move forward. Haber is more famous. Any movie you've seen where the guy is like a German scientist who's evil, who's wearing that monocle, that's Haber. That's who they're making. He was a chemical weapons guru, for better or worse. If you want to be depressed and do him, somebody's probably already asked, and they've gotten me responding saying, oh, are you sure you really want to go into that deep darkness? If you're somebody who's like, yeah, just be warned, Haber is a very famous chemist, and actually his wife was too. Very fascinating. So if you want to go into some deep dark doo-doo, pick one of them. All right. Unless somebody already has. So let's go back up here. When we put it on ice, it went the wrong way. We're trying to make it go forward. So heat. Yeah, heat makes it go forward. So heat means high temperature. So you can either write high temp or you can write increase in temperature. So high temperature. What about pressure? Well, if we increase the pressure, it did shift it forward. High pressure moves it towards the side with fewer moles. So big disclaimer we have to do here. We're going to do a couple other practice throughout this video. Might be split into two. These are independent of each other. You can have high temperature, high pressure, low, low, high, low, low, high. Again, temperature is determined if it's exo or endo. So endo likes high temperature, and pressure is determined by the number of moles of gas. So pressure and volume are related, but pressure and temperature are not with any of this equilibrium stuff, which is what we do this term. All right, and then the last one. What if we increase the temperature, what happens to K? So in the first video I talked about, the only thing that changes our value of K is temperature. And it depends if it's exo or endo. So as we increase the temperature, it was endo, it shifted forward. So high temperature shifts forward because it's endo. I think you can see this. Yes, you can. If it shifts forward, that means you're going to make more of the products. And since it's a ratio, we've shifted towards more products. So that's going to increase K. Again, temperature is the only thing that changes K. All the other ones come to a balance point. A change in volume and pressure actually changes the concentration. And so that's why it shifts it, because it does change these values, and K has to stay constant. The only thing that affects the value of K is temperature. And that brings us to the next one, the last one on this page. All right. And again, if you didn't get it from the last video, you gotta print the notes or somehow have them in front of you as we're going through this. All right. Can you guys see me over here? Yeah. Hopefully. All right. You know what? Let's turn on the light. Does that help? No, it might make more of a shadow. All right. So NO2, these are gases. Used to have this demo. And then one day I went in the back room, this is 25 years ago, and it was broken because it was a closed system, and that scared me, whoever broke it. I don't know if they're still alive, because this is one of the most toxic gases that there is. It's brown, it's awful. In the atmosphere, nitrogen and oxygen, whenever there's a lightning storm, whenever a high amount of electricity goes through, they react and they form so many different things. And one of them is NO2, which is really bad and toxic. You're outside, it's going to go dissipate. Anyway, so depending on what color you see, you can determine what's going on. So somebody did this experiment and they determined that at 273, the value of K is this, and at 298 Kelvin. So when we increase the temperature, K decreased. Well, if K decreased, that means it shifted in the reverse direction. So remember, K is a ratio. Whenever K decreases, it must mean that you have less on top. If K decreases, that means you have less of the products. I know I just wrote really small, but you can rewind it, go back 30 seconds, and listen. So temperature made K decrease. Higher temperature, K decreased, which means there's less product, which means it shifted in the reverse direction. Temperature loves the endothermic direction. The reverse direction is endo. Our reaction is exo. So whenever it asks is it exo or endo, it's asking in the forward direction. That would mean the heat would be on this side. It's releasing heat. It's a negative delta H. You're losing heat. So as we add heat, it's shifted that way. Decrease the N2O4, increase the NO2, the ratio decreased. All right, so Santa's elf gets a hold of this demo and plunges it on ice. So heat is here. It's going to make it go in the forward direction to try to make more heat. So it's going to become colorless. So often it's just forward, reverse, we're just doing the arrows. But sometimes you will see where the question's going to make you figure out forward or reverse. And then since it went forward, it turns colorless. All right, what happens if we increase the pressure? If you increase the pressure, again, it moves forward. Because this side had less moles. That had only 1 mole. 2 NO2, that's 2. Versus 1, it's just forward. Again, it goes to colorless. This is a really cool demo that I've never actually done. And so hopefully I'm going to find it online while I'm on my break that I'm not really getting this year at all. But it is, yeah, I have an attitude about this, what's being expected of teachers. But you increase the pressure, you push it together, and the color disappears. So most people think about it artistically. If you concentrated it, it should get deeper and darker brown. Actually, the color disappears because chemically, it's going to shift to the other side. And that side, the color is natural to that compound. And so it just pushes all the brown into a colorless compound. All right, we're going to do one more question that I don't think is on there. What temperature and pressure will make it colorless? Well, we would want, in this case, low temperature and high pressure. Those are the conditions that made it go forward. You're pretty much always asked what will make it go forward. So again, I just wanted to show that these two are totally independent. And all right, if you have questions, write them down or rewind and go back and write them down. And you come to office hours and you say, Dr. Sherpa, can we go back over page 4 of the Le Chatelier's? But by then we may have gone back and you can do it again. I recommend you do the notes twice. All right, we're going to do page 5. I have a handy dandy second board that we'll put in front of here. And maybe my shadow is going to go on in front. My shadow's help. All right, let's see. So manipulating K. We can erase all the other stuff above it so you're not confused. We're not stressing it. We're just going to manipulate it. There's the gnomes dancing up there. There's the gnomes up there. And, all right. So we're going to manipulate K. This is our starting point. And then what happened here? All I did is I flipped the equation. So when you flip the equation, so my product became the reactant, you flip K. Why? Well, if we wrote our K expression, initially it was HI on top over hydrogen times the iodine. When we do this equation, I'll call it KR for reverse, you now have the hydrogen and iodine on top over the HI. So I flipped it on its head. Do you want me to do the headstand? I could. Which means you would do 1 over K1. I'm going to write it like this. There is a number given to you. I want to mention, you will sometimes see where I don't give you numbers. I want you to write it as an algebraic expression. So it's just 1 over K. It's in your calculator. Or you can write it as K to the -1. I mention that because you're going to have multiple choice at some point. And you have to know, if you write it, I don't care, I know both those answers. But you would only have one of those choices. All right, let's look at this one here. Compared to our original, we doubled. So if you double, what's going to happen? Well, this becomes to the 4th power, this becomes the 2nd, this becomes the 2nd. You're not doubling K, it's an exponential. So you're taking the original K, and you're not doubling it, you're squaring it. So however you affect the equation, that becomes your power. So this is actually a lot of teachers, and again, most of you have had other teachers. I think of it as flipping because that's how my mind thinks, inversion. A lot of teachers will teach us as multiplying this equation by -1. And so the exponent will become -1, which means the products become the reactants and stuff. All right, here if we double, that becomes our exponent. So let's do the next one. So you can pause me and try it, or you can keep going. So oxygen makes ozone. O3 is ozone. And I'm going to talk about values of K in a moment. This means this doesn't happen. That K value is so small. So remember, K's are always positive, but they can be big or small. K of 1 doesn't mean anything. I've never seen anything with a K of 1. It doesn't mean perfect balance. Everything has its balance point. This balance point, it's so much favoring the reactant. There's so much oxygen and hardly any ozone. There's like 1 molecule of ozone for every Avogadro's squared of oxygen. It's really hard to make ozone. That's why the depletion of ozone was so worrisome, is so worrisome, because it takes a while. There was a hole. It only lasted like a couple days. It was right at the end of spring term. There was a hole over the North Pole, so poor Santa's elves. But it closed itself, and that was due to something, somehow how the winds and stuff were. All right, so what happened here is, compared to the first one, the reaction is 1/2. So I cut that in half, so I have 3 halves. I cut that in half, so I have only 1. So what are we going to do to K? We would take K to the 1/2. Got it? Really simple. It becomes the power. The other way to write this, just to make sure, 1/2 means the square root. So you could also write it like that. And again, I don't care which way you write it. When I say show me the symbols first, that's what I mean. And then you give me your numeric answer. And again, you will see in multiple choice where there won't be any numbers. You're just working with the algebra. All right, we're comparing again the first equation to this one, and all we did was we flipped the equation. So we flip K, so either K to -1 or 1 over K. again, means the same thing. So inversion. All right. So speaking of inversion, we don't stand on our heads, or I can flip the board. That's what magic wands do for you. Can you see the whole board? Hopefully you can. All right. I lost the black pen, so you don't have to deal with blue. So this is what I've been promising, and I have been talking about. What does K tell us? K is, again, it's a ratio. K is always products over reactants. It is a ratio that tells you which you have more of. It is a constant. Because something has a ratio of 1 doesn't make it perfect. Everything has its balance point. And so you'll find our balance. So here, if K is greater than 1, that must mean you have more products. I'm just going to write P, or it favors the forward direction, or it favors the products. So again, this is not shifting. Le Chatelier's principle was shifting. Something had a balance point and we stressed and had to shift to get back to that balance point. This is an actual value of K, and it favors one side or the other. The only time it wouldn't favor would be a 1, and I've never actually seen a 1. If K is outrageously huge, which happened for the problem, the previous problem when the ozone breaks down to oxygen, you get this crazy number of like 10 to the 50th power, like bigger than Avogadro's number. When we get that big, it's pretty much, it's a one-way reaction. One-way reaction. Because it's all products. How can they even, there was like 1 molecule of ozone and all the rest was oxygen. All right, so then these guys, if K is less than 1, it means you have more reactants. There's more in the numerator. Less product, more reactants, or it favors the reverse direction. Thankfully, reverse and reactants both have an R, so we don't get confused here. So reverse, the reactants are favored. If K is very, very small, it means there was no reaction. I'm going to put a question mark. And if you go back to the very first question on the ozone, 10 to the negative 58th. Really? How can you even measure that number? We put these numbers out there and they're actually mathematically can't be figured out. It's so small. That's 57 zeros, 0.0000000. Those here were with me in 221. Remember I put all those 9s, 99.9999999. That's like what it's going at. We're emptiness. Matter doesn't exist. How are you even seeing me now? Put your hand through me. Oh wait, I am virtual. So I'm not real. All right. Let's do Hess's Law. I love Hess's Law. There are, I think, 9 of you who learned Hess's Law with me back in 221, back in the days when we were all together. I'm like real. We are still real. All right, let's look at these numbers actually. 7.9 e to the 11th. That just means it's product favored. It's the exponent, tells us it's product favored. Negative exponents mean K is less than 1. These are reactant favored. So you're just going to tell me product favored or reactant favored. You don't have to go into the one way and no reaction. But really, this K2, that's not going to happen. Hydrogen does not want to be by itself. Now, in space, there is so much empty space that you never find hydrogen as diatomic because they never come near each other. But when they do, they form the diatomic. There's more empty space in every atom that makes up every cell, every molecule, every cell, every part of your body. There's more empty space than there is in space. Think about that. All right. And then we go inside of that and there's more empty space. So we're trying to get to this equation. And again, most you learn from other teachers, and if you like how they did it, the key is the last point. What I do is I find the piece in each equation that I need. I need the HBr from my first equation. I cannot change this equation that I'm trying to solve for. I can change the others. I need just one. So I'm going to have to cut this equation in half. Half a hydrogen plus half a bromine gives me an HBr. It doesn't mean I cut this in half. Oh, I do K1 to the 1/2 power. Hess's law with K's. So don't cut K in half, take it to the 1/2 power, or you can take the square root. Either way. All right, the next one, I want the hydrogen, but just as H. It's on the wrong side, so we got to flip it and cut it in half. So we have to get it so it goes H to half a hydrogen. So we're going to flip it and cut it in half. So it would be K2 to the -1/2. And we do the same for this one, which would be K3 to the -1/2. Now, the big point is, again, whatever you do to the equation, you flip it, becomes a negative exponent, you cut it in half, becomes a 1/2 exponent. So steps 2 and 3 will be to -1/2. I'll show you another way to write it. When you bring them all together, you don't add, you multiply, because it's a ratio. If you go back and look at how we wrote all our K's, we never added. We always did a ratio. So what this becomes, I'm going to show you 2 ways you can do it, is everything's to the 1/2, which means we have a big square root. K1 was a positive exponent, and K2 and K3 would be in the denominator. That is one way to write it. So the square root, the net K, is the square root of K1 divided by K2 times K3. Or you could write it as K1 to the 1/2 times K2 to the -1/2 times K3 to -1/2. I can write over here because you can see up here. So again, you can write K1 to the 1/2, K2 to the -1/2, K3 to -1/2. You write it like that. Turn off my glare, get out of my shadow. That's what our K net was. You're multiplying all the K's together, or you can write it as a big square root, K1 over K2, K3, all multiplying. So negative exponents mean they become in the denominator. They were all to the 1/2. And that, my friends, do we want to... All right. So the next 3 pages are practice problems. What you need to do is stop me, try the problems. I'm going to walk through them just very briefly and give you a hint of how to do every one of them. And great, so I'm going to stop. I'm going to do it with that little overhead thing. So blessings and blessings, and